physics. He has also a lot of experience coming from his long years at Hurth, organizing different workshops, and as a last thing, he has become a professor at the University of Mainz. So I am sure we will benefit a lot from what he has to teach us.
Okay, thank you very much for the invitation. I was asked to give you lectures about flavor physics, and this means for me that I will explain for flavor physics. This means the mechanism. So this will be based on what you learned about the standard model last week. Then, of course, what is most of interest is for us now what we can learn about new physics beyond the standard model from flavor physics. And there's another topic I want to do is neutrino masses. So that's definitely one sign of new physics which we have already found beyond the standard model. And I just want to give you the basics about how to implement neutrino masses in the standard model, or what I have to do in addition to get neutrino masses described by a slightly extended standard model.
By the way, I don't think your microphone is on.
It doesn't work?
Okay, that's good.
Works now? It's not working yet.
Now it works. Okay, now it's better. Good. So, obviously, because we're working and now it doesn't work. You sure this works? You do that? Okay. So, because we do flavor physics, the selected number of topics I will show you depends, of course, on the flavor of the lecturer. And so this means neutrino physics, MV meson physics, Kanon physics, etc. And I give you a complete coverage is given to you by reading this, which you will see at the end of the lecture. Then I want to invite you to ask as many questions as possible, so please feel free to stop me at any time, right? I think I'm not allowed probably to say this, but you asked not much questions compared with other schools I know, so take the advantage and interrupt me at any time, right? So, I have to ask you, I see, okay. So just a prologue, standard model of elementary particle physics. You learned about the fundamental forces in nature, that they are governed by the local gauge principle, which are governed by these three gauge groups, and this allows for a unified description of all the interactions. And then you have the building blocks of matter, which are given here in fundamental families, the first, the second, and the third family, which are doublets regarding the SO2 or singlets regarding the SO2. And we have no idea why we have two, or the third family, where they come from, who ordered them. And the question which flavor physics deals with, just to give you a definition of it, is that part of the standard model which differentiates between the three families of fundamental fermions. So what are the differences between the first, the second, and the third family? Okay? And the first thing one can say is that mainly the mass parameter, the mass quantum number, is different for all these three families here. Okay? So the main success of the standard model, just to give you a repetition of what you have learned last week, we have all gauge bosons found in the experiment. The electric position measurements have confirmed the standard model predictions in the gauge sector to the promille level. Next, please. And the weaknesses on the standard model, I think you also learned, is that the Higgs bosons not found yet. There are other possibilities to describe electroweak symmetry breaking besides the Higgs boson mass, of course. And there are many free parameters, and those parameters are mainly in the so-called flavor sector of the standard model, where masses of the fermions, mixing matrices, etc. Then curvature is not invoked in the unification, and then you also learn there is a possible unification between electromagnetic weak and strong force. There are some indications. The first one is more theoretical, that the three gauge groups nicely fit into higher gauge groups, and there is a kind of unification of the coupling constant at the high scale. So, of course, and there's also a problem which was discussed last week. This is the called hierarchy problem, that when you introduce a fundamental scalar in your theory, then you get quadratically sensitive to the highest scale in the theory by radiative corrections. Okay? So that's not the problem of the standard model, but if you implement the standard model into a higher theory, which involves, for example, the Guth scale or the Planck scale, right? Then it's not clear why the Higgs boson mass stays at the standard model scale, where you need it. Okay? So the standard model itself is completely fine for itself. However, when you assume that the standard model is only an effective theory at the low energy, and we have at the Guth scale and the Planck scale more particles, more degrees of freedom, then they would add here large contributions to the Higgs boson mass, and then it becomes complicated to understand why the Higgs boson mass is here at the standard model scale and not at the Planck scale. Right? Now, there is one thing which you keep in mind, that we assume here that we have a weakly coupled theory from the standard model scale to the Planck scale, and I think you should be skeptic about this. This is a very strong assumption, because when you go into the other direction, right, and see about how many orders of magnitude of scales we go into the other direction, and how many layers of different theories we have, they are found year by year or century by century, I would almost say, then I think it's a big assumption about this thing, that we assume that there's a weakly coupled theory from the standard model up to the Guth scale. Right? I'm going to go back. And I would say the following. So when you look here at unification, and probably this is one indication that the assumption that we have a weakly coupled theory to the highest scale, and we don't regard it as an accident, what you see here, and this is an indication for the fact that the hierarchy problem is probably really a problem, right? But it's only an indication for this. You understand what I want to say, right? So it's a big assumption to assume that there is a weakly coupled theory to the very high scale. Here we find now that these gauge groups meet, also under this assumption that we have a weakly coupled theory to the high scale, and then this becomes a problem, what we call the hierarchy problem. Next slide again. So only when we have a weakly coupled theory, this is a problem, right? If we have a strongly coupled theory just above the standard model level, then this problem is not there, right? One should keep that in mind. There's a comparison. Of course, this hierarchy problem has to do that the Higgs particle is a scalar. So that's why people say probably we have no fundamental scalars, because at the photon and the quark masses, we could also have large contributions from radiative corrections here. However, here we have the gauge invariance, which keeps the photon mass to zero when you take into account the radiative corrections. And in the quark masses, you have the chiral symmetry, also another symmetry, which is a symmetry in the limit of the quark masses to zero, which protects the quark masses from large corrections. Right? And we have not such a protection in the case of the Higgs boson mass in the standard model. So there are many solutions to this hierarchy problem. It was a guiding principle for model building, little Higgs models, extra dimensions, and supersymmetry. Right? And supersymmetry is somehow the nicest one, because here you have a complete cancellation of the Higgs radiative corrections on the standard model side and the supersymmetric side, or from the superpartners. However, we have found that the superpartner masses are much larger than what we have found already for the top mass. So it's clear that the new physics scale somehow has not allowed to be very large, because if these masses are too large, then we have a breaking or radiative correction which go logarithmically, and the mass is not allowed not to be larger than somehow 1 GeV to solve that problem. Okay? So supersymmetry is only a problem when this mismatch between nanomolar particles and superpartners is not too large, and all superpartners somehow occur at the 1 TeV level. Generally, if you don't think about supersymmetry, you see that this is a pre-level contribution of the Higgs particle mass, and then you have new physics contribution, and then when this should not be too large, then the new physics scale has to be at the 1 TeV scale to care about this problem here. Okay? Good. Next problem. I just want to say there's another problem here. When you look at the electroweak precision measurements and see what they indicate for new physics, then you see what we call the little hierarchy problem, that new physics should occur at earliest time at 3 or 10 TeV. This comes from the constraints we have on the electroweak precision data. As I told you at the beginning, we have found that the electroweak precision data is good at the 1 per mil level. So the Stone model is good to a very, very high accuracy. There is no space for new physics contributions. So this means that new physics cannot start earlier than 3 or 10 TeV. So that's what we call the little hierarchy problem. So this is a highly non-trivial constraint on the possible new physics. Right? So it has to find some extra symmetries or whatever, which allows new physics to be at the 1 TeV scale. And there's yet another way, indirect way to look for new physics, and that is flavor physics. See the next slide. And what is flavor physics? As I told you, it's that part of the Stone model which differentiates between the 3 fundamental platinum families. Right? So what are the differences between those? And you learned already that if you look at the charge interactions with W in the weak interactions, that there is a mixing matrices between these 3 families of quarks. This is described by a 3x3 matrix, which is called the CKM matrix. And of course, it's a base transformation. It means that it has to be unitary. So there are, when you have a unitary 3x3 matrix, you have 6 relations, right? The rows, for example, have to be orthogonal. So one of those relations, unitarity relations, is this one here. So there are 2 rows in this unitary CKM matrix. It has to be orthogonal. And these are just 3 complex numbers, and these 3 complex numbers you can write down can be written in a so-called CKM unitary triangle. So this is the one side here is normalized to 1, and this is just 3 complex numbers. The first number, the second number, plus the third number gives 0, right? So you see where the CKM matrix unitarity relation comes from. Okay? So we have one relation from the unitarity, and you can write them down here in a triangle in the complex plane, right? Because the sum of 3 complex numbers gives you 0, and this is exactly here illustrated by this unitary, so-called unitary triangle. And you should keep in mind that there are 6 of those, right? Because you have a unitary 3x3 matrix, you have 6 unitary relations, and this one is the most famous one. The reason will come clear later. And then what you also learned already, and we will work that out in this lecture, is one parameter in the so-called CKM description which is responsible for CP violation. This is the so-called J, stands for the Jalskov parameter, and this is just one phase, complex phase in this CKM matrix. And this is a very predictive theory that you have only one parameter which is responsible for any kind of CPU violation which we find in nature. So that is a very predictive part of the standard model, and we have to see how good this is, right? And I think we have now a history of 10 years of B factories where this was confirmed, right? So that's the crucial point. Next slide, please. So that is a matter what I want to say in my introduction, that all present measurements, so Bava and Bell are the B factories which were built to test exactly this description of flavor violation and CPU violation. And there was before there was a Cleo measurement, but they also at the Teletron, CDF and DCO, they were being able to make a lot of flavor physics experiments. So rare decays means that the flavor parameter gets only changed by 1, or mixing phenomena where the flavor quantum number gets changed by 2. or any kind of CP-related observables, they're all well described by this very simple flavor mixing description, just by this 3+3 matrix. And CP validation will all described by this one parameter, which is one place in this mixing matrix. This is all consistent with the CKM theory, and this was somehow also surprising. First hand, of course, it's an impressive success of the standard model and the simple CKM theory, because before the B factories here 10 years ago, there were many other possible theories of CP validation, right? Which were more complicated. Here's the simplest one, namely describing all CP validating phenomena by one parameter, as was all confirmed by the Barber and Bell experiments in the last 10 years. That is somehow unexpected. Let me go to the next slide. Because normally you would expect that you are really sensitive for new degrees of freedom. And this I want to explain to you now. When you have flavor changing neutral currents, and you learned that in the first lecture, I have just looked it up, so you should know that. So you don't have any kind of flavor changing neutral currents on the tree level. So when you look at this standard model, you want to look at a flavor change from B to S, right? Which they have the same charge here, right? So this is a neutral current, B to S. Okay, there's no charge change. In contrast to this one here. Here you change the charge by 1, by the W. Here, this is from B to S and a gamma. This tree level coupling is not existing on the tree level. You only get it on the loop level. So you need a W and a top quark here as a virtual particle to produce a flavor changing neutral current. Okay. So even in the standard model, this flavor changing neutral currents only occur on the one loop level. Okay. There's no tree level coupling B to S gamma. So now you can hope for that if there are new degrees of freedom, let's assume this, and they are just around the corner. That's what we expect from LHC. So what we want to do at LHC, we want to go up with the proton-proton, or here we think that's what more about it, plus and minus, and you have go up with the energy to produce these new particles, right? Particle-antiparticle pair, and show the existence of these new particles. However, you need high energy for this, and you know what was the price for the LHC, so you have to invest a lot of money. However, before you can do this, you can hope for that these new degrees of freedom, when they exist, they also contribute to this flavor changing neutral current. Because there are new virtual particles here, and if they exist, they also contribute, one or the other way, to this B to S gamma decay mode as virtual particles. And then they should contribute somehow at the same level than the standard model. Okay? So when you compare this with electroweak precision data, then normally you have in the electroweak precision data, you have a tree level contribution from the standard model, and you have a loop level contribution from the standard model, and then you have new physics contribution virtually from the new physics contribution. Here, you're much better off. Here, the new physics contribution, if it exists, directly contribute the same loop level than the standard model contribution. You see that why people have assumed or expected that this is a highly sensitive probe for new physics. Okay? But it turned out that specifically B to S gamma, I will show you the data later on, is nicely compatible with the standard model prediction. And I don't need any new physics contribution at the moment. Okay? And that's what we call the flavor problem, but we'll come to this later. Yeah? You see what makes it the result that this standard model contribution describes the B to S gamma data very well is unexpected. You should have to wait. Next slide, please. Now, of course, there are other ways which have confirmed the standard model. So here you see the triangle. This one is normalized up to 1, and this is one of these unitorial relations. And in some sense, this triangle is fixed when you have fixed this one point here. So this is normalized. And then if you have fixed this one point in the complex plane, this unitary triangle is fixed. It turns out that the sides and also the angles are directly observable. And then you can use different experiments here, epsilon k, sine to beta, that is the main B factory data, or delta MD. I don't want to go through the details of different measurements. You see, what you see here are just the arrow bars of the different measurements. You see that they're all compatible with fixing this one point of the triangle here in the complex plane. Okay? They're all compatible with each other. Right? So it's described by this one unitary relation. Now, next slide. It's even more convincing because when you separate things from CP conserving and CP violating observables, you can think, okay, if the CKM matrix is not responsible for CP violation, as I told you already, we will explain this in detail in a minute, then there should be a difference in the fixing of this triangle when I look at CP violating and CP conserving observables. But again, the fixing of this point here is always compatible with each other at the 1.9 sigma level. Okay? So even if I separate now between CP violating and CP conserving observables. Next slide. And then even more convincing is when I look at three processes, so processes in flavor physics which start on the tree level and things which start on the loop level. Because I told you, on the loop level we expect that there are new physics contributions. But we do not expect high contributions from new physics in tree level processes. Okay? So if there's new physics around the corner, right, there should be a difference in fixing this one point in the complex plane, yeah? Fix this one unitary triangle, which is one of 6 unitary triangles. However, if you look at the tree processes, which is given here by gamma and the VUB, which also can be fixed by a tree level process, you compare things with sin to beta or delta MB, which are governed by a loop process only, then you see that also again they're compatible with each other at the 2 sigma level. So there's no sign of any deviation from this very simple CKM description of flavor mixing. Okay? And CP violation. Next slide. So most surprising, just to emphasize this again, so you can, for example, fix symplectonic tree decays, just as an example. Here you can look at BU lambda. This is a lepton, charged lepton, and a neutrino. This we call a symplectonic tree decay. This is completely standard model dominated because the tree process, there's no chance that new physics enters here. And then we have a loop process like neutral meso mixing, right? B to B bar. And you see here, this is only induced in the standard model by a loop process. Okay? It could be possibly, like in the beta gamma case, new physics decrease of freedom here, which gives you an additional contribution. However, the fixing of the CKM matrix elements of this loop process are nicely compatible with the fixing of the CKM matrix elements from the tree level processes. Right? So that's the surprising point and the surprising, convincing result of the B factories in the last 10 years. Okay? Next slide, please. So, what I also say again, there's much more data not shown in the neutrality fits which confirm the standard model predictions. And I showed you one already, which is beta gamma, but I'll give you the precise data later on. So there is a completely convincing picture now of flavor mixing by the standard model. However, we know that there must be new physics contributions for one or the other reason. For example, to solve the hierarchy problem, as I explained to you before. So there is a problem for us, right, at the moment, because we expect somehow new physics contributions to high level, right, contribution to these flavor changing recurrence, to these flavor observables, which are used only at the loop level, but we haven't seen them. So if there's new physics around the corner, how this outcome of the B factories can be interpreted. That's the main problem. Okay? So before we discuss this, we should say that the Nobel Prize 2008 was given to this, or half of the Nobel Prize was given to these two people here, Kobayashi and Maskaper. And this is a nice work which is nicely, was written here in 1972. And it's very convincing because at that time the Weinberg-Salam model had only 2 families. Okay? There was no third family. And we will learn that CP phase is only possible when you have 3 families. When you have 2 families, you will see there's no complex phase possible in the mixing matrix. So when you have only 2 families of fundamental fermions, and the mixing matrix cannot describe CP violation. Okay? What these gentlemen did at that time, they looked at the Weinberg-Salam model of this time with 2 families, and said how I can implement CP evaluation in the standard model, because it was clear from KL mixing since the 60s there is CP evaluation. So the standard model should describe CP evaluation. So they went, next slide please, through these are the whole paper, yeah? So all possible ways how to get a CP phase into the standard model. So they have extended the Higgs sector, they have extended the gauge sector, and then we have additional mixing matrices, which could describe CP evaluation. And the last option, right, next slide, was, and you can see this here, next we consider a triplet model. So we postulate there is a third family. And when there is a third family, then we have this mixing matrix, a 3 by 3 matrix, and then you have one physical phase involved. Okay? And then you can describe CP evaluation by the standard model. But there are many other options. So when the Nobel Prize Committee says they have predicted the third family, this is a wrong statement. So they looked at all possible ways to extend the standard model at that time to get a CP phase, right? And one of those, and I think it was just the last option they have written down, was third family. Okay? So that's why they got the Nobel Prize. However, there's a nice, interesting statement to say the first time when the CKM matrix, mixing matrix, was written down, it was not unitary. So there was a typo in those, so they had to write an errata. Right? So even if you make little mistakes, right, don't worry, it doesn't keep the Nobel Prize away from you. Okay? So next slide, please. Okay. So we have learned from the B-factories, the CKM mechanism of mixing is the dominating effect for CP evaluation and flavor mixing in the bulk sector, but there is still room for sizable new physics and new flavor specters because, and that's what I should emphasize now, we have measured the flavor sector only to the 10% level, so there is still something possible. There are no order 1 corrections, but at the 10% level there is something left over. And of course the standard model does not describe the phenomena like neutrino masses, so we have to talk also about this, how to extend the standard model. Okay. So let's come to the flavor problem of the standard model. What is meant by this? And I think this you understand easily. So you look at the standard model Lagrange, you have a gauge part and a Higgs part. Okay? And the gauge principle governs the gauge sector of the standard model. So as you have seen in the standard model lecture, everything is fixed by the gauge principle. The interactions of the gauge bosons with the fundamental fermions, everything is fixed. Right? And there are only 3 couplings involved, and everything else is fixed. However, in the Higgs sector, this is not true. Let's go to the next slide. There's no guiding principle in the flavor sector. Here, we have mixing matrices, we have 3 Yukawa standard model couplings, which are not constrained by gauge invariance. So it's just a most general 3 by 3 matrix which you write down there, right? So we get a lot of parameters, standard model parameters, which have to be fixed by experiment in the standard model, are all flavor parameters, right? There are the masses, or for example, the masses and the mixing parameters, which all have to be fixed, and we have no deeper understanding of it. So the description by the CKM matrix and by the masses of the quark masses is practically very good, right? However, we have no deeper understanding where these parameters come from. And the crucial thing is, please next slide, or next contribution here, is, for example, the CKM matrix, you see, has a hierarchical structure. So they have diagonal elements of 0.2, and then if you note the non-diagonal elements, they differ by 2 orders of magnitude. When you look at the gauge couplings in the gauge sector, you see they're all of the same order, and even have the nice property to go to one point when you go to the unification scale, right? So that's what we call the flavor problem of the standard model, that we have no understanding where this hierarchy comes from. So there is definitely a guiding principle missing in the flavor sector, right? And we have no deep understanding of it. It's not clear that we ever learn this soon, right? Because it could be that this flavor symmetries is created or broken at a very high scale, but it's definitely a problem, and which results in this large number of unexplained parameters of the standard model. Okay, next slide. There are many open problems, questions in particle physics which are related to flavor. Just should not understand everything here. Clearly, the question is why we have 3 families. So there are a lot of papers now recently why there should be not 4th family, right? And then the phenomenon was worked out for this case. Then how neutrino quark masses mixing angles are generated. That's what I call the flavor problem of the Stunner model. We have no deep understanding, no theory behind this. Then, do there exist new sources of flavor in CPU relation as we hoped for? Are there new contributions from new other flavor structures like quark mixing in supersymmetry or whatever? Is there anything beyond CKM and something beyond the Janssen parameter? At the moment, we haven't seen any sign for this. Keep that in mind. And then is there a simulation of the acoustic gauge sector? I think it was mentioned at least once last week that in principle there would be also a simulation possible is the acoustic part. There is one circulating parameter invoked, and we do not know why this has to be small. This is sometimes called as CP or strong CP problem. And of course, when you look at gut series where the fermions get unified, the leptons and the quarks, you can ask yourself how the flavor structure of the lepton and the quark sector is related. And at the moment, it looks like that the hierarchical structure of the quark sector is not reflected in the neutrino sector. And I will come to this later on. Okay, now come to the next slide. So let's start with B meson physics now. The prologue, what we can learn from B physics. So what we looked at B factories. There is some nice features, of course, is that the B quark is the heaviest quark with pronounced hadronic bound states. So we can make strong QCD tests. And because the mass of the B meson is so large, there are a lot of decay modes, so you can fix many parameters of the Stunner model, because you can access many CKM parameters. That's one thing. And then Jim suppression largely relates because of large top mass, and we'll explain this in a second. And then, of course, it's an independent test of the mechanism of CP violation, because until then it was only found in the cable system. There were large effects that are expected in the B sector. In the cable sector, they are small, and they are somehow also hidden by long-distance QCD effects, and which are much better under control in B physics. Next slide, please. So let's explain what means Jim mechanism. Jim mechanism has directly to do what I call the CKM unitarity relation. You see the unitarity relation is given like this. This is this term plus this term plus this term gives 0. Just to remember. Okay. Now let's look at the flavor change in neutral current B to D. Okay. How this is possible. Probably there is a W here and a gamma, and you look at B to D gamma. But it's enough to look at this one line because there was a green line here, but you cannot see it. Right? But the crucial point is this line here, the flavor line. Okay. So you can see that this is probably a W, a gamma. But if a B changes to a D, you need two CKM matrices, because you have to go to the loop level. We learned that just before. And then you have UB, UE, and of course, in the loop level, the U, the C, and the top quark can contribute. Okay? All three quark families can contribute here. Okay? Now, it means when you calculate this diagram here, or this diagram and this diagram, it's all the same function, because the only difference between the upper quark, the charm quark, and the top quark is the mass. Okay? So you could calculate this diagram here, and this gives you F of mass, that's the MU mass, and F of C mass, and F of the top quark. So F is just a function which is fixed by this diagram here. And then in front of it, it's governed here by the CKM matrix elements, which are all look the same, up to the fact that there's a U here, a C here, and a top here. Okay? So the fact that when the masses are all the same, or all 0, then all these factors are the same, you can take them out, and then you have just a unitary relation, and then the amplitude would be 0. Okay? So, Jim suppression means that these things are only non-zero because of the differences of the masses. Right? That's what we call Jim at the loop level. Okay? This is from Iopoulos, Garni, and Green is we've presented both of this. They predicted the charm mass for this, but it's important to see that at the loop level it explains that all these flavor change intercurrents are only possible because of the differences in the masses of the three fundamental Tamian families. Okay? Now, however, the top quark mass is much larger than the charm of the upper quark mass, And this means that this contribution here is definitely dominating, and this is what is meant with that the large top mass overrides the Jim mechanism, or Jim expression. Okay? However, now it depends strongly how this function here depends on the masses. If it's quadratic, then of course the top walk squared is definitely dominating the other two parameters here. If it's only logarithmic, then also the charm mass contribution plays a role. Okay? So that is what people call quadratic Jim and logarithmic Jim. Okay? One should keep in mind there are always contributions which are mass independent, which of course contribute to all three sources. All three. Right. So the central question in physics is, as I said, CKM chronology, mechanism of circulation, indirect search for new physics, and of course we want to better understand the strong reactions. This of course we have also can be explained. And let's go to the next slide and start with circulation or unitary triangle. So why we want to do this? We want to determine the fundamental standard model parameters, which we do not understand, right? So that's why we do CKM chronology. As we said, this is this 3x3 matrix described by this triangle here, and this is one of the relations here which you get out when you take this one and B and D. Right? So this row and this row gives this. They have to be orthogonal. That's right. And there's another parameterization of it which shows you the hierarchy that these ones are order 1 and the non-random elements are much smaller, 1 order, 2 order. The other thing while we are looking at CKM chronology is that CKM phase is the only source of circulation, and over-constraining the unitary triangle, as we have seen in this triangles in the pictures we have seen before, is a good way for search for new physics. Unfortunately, we haven't found any alignment of these different constraints of the unitary triangle, as we have seen before. So we have found many constraints for the same parameter, and all turn out to be congruent with each other. Okay. Next slide, please. So circulation, why this is interesting, as I told you, there's one parameter only in the standard model. So only one circulating parameter. It's very predictive, and it was confirmed by the refactory data, and this gave the Nobel Prize for all these people here. Right? And there are also some Tobias switches which are theoretical very clean because polygon uncertainties drop out. It's a more technical point. Right? And there's another point when you look at baryon asymmetry. That has to do with the fact why we have built out of matter, and there's a mismatch between matter and antimatter, right, in our universe. That's obvious. To explain this, one definitely needs new sources of circulation, right, which go beyond the sources of circulation which are offered by the standard model. However, this argument is always used, okay, at refactories, we have to find new sources of circulation beyond the one in the standard model. However, this argument is not so strong because these new sources of circulation are not necessarily relevant at the low energy where we do our experiments at the moment, right? They solve this baryon asymmetry problem also when they are only active at a very high scale, which you cannot access by the present experiments, right?
Do you know the scale? What's that scale, roughly?
I think that this is not fixed, right? So it could be much larger, could be at the gut scale, right? So you don't have to be active here at the low scale, right? You need new sources, but after the Big Bang, you need many sources of circulation, which definitely more than what is offered by the standard model, that we know. But at the conditions which were after the Big Bang, I think very high energy. So I think it could be that there is constraint.
Like what we guess, like a few seconds after the Big Bang or whatever, the CP stopped.
Right. Yeah, I think you're right. There must be a constraint on the energies, right? So it should be, but I think this I don't know, right? But there must be. I'm not an astrophysics physicist, so I should give you a number. But what it turns out, it could be at a very high scale, right? And the important thing for us is this argument is always used for the motivation of the refactories, since they say, look, we have to find new sources of circulation. This was the wrong statement, right? So of course, for the funding agencies, it's nice, right? You said, well. But it definitely was not a win-win situation because there's always one way out. That you can go to a higher scale. If you do not access by the refactories, but do not access by LUC either, right? So you can go beyond 100 TB for sure, right?
Can I
And
give
it's not
you
relevant.
an example as answer? If you have biogenesis via leptogenesis, via decay of right-handed neutrinos, you could have right-handed neutrinos, just if you plug in the seesaw expression, you could have them at 10 to the 14 GeV, but you could have them much lighter. You could have them at TeV scale too. And you only need to generate the lepton asymmetry above electroweak symmetry breaking scale so that it can get converted into baryon asymmetry. So that's just an example. The asymmetry somewhere, above the electroweak scale, up to close to God scale, and it's not fixed by experiment.
Because that has now, when you go to lepton genesis, then it has to do that. It's very difficult to test evaluation in the lepton sector, right? So then we'll come to this tomorrow, right? That's a good example. But if you stay in the quark sector, that's one question, and then if you go use lepton genesis, then of course you can escape completely because it's very difficult to test the CP phases, additional CP phases in the lepton sector. Okay, let's come to the next point. And of course, the crucial point is that there are various extensions naturally in any kind of new physics model. So if you go to supersymmetry, which many people now take this as the extension of the standard model, which solves a hierarchy problem, which we discussed before, right? In this model, in principle, naturally, you have 45 phases for CP evaluation, right? Just say that. In the standard model, you have one, and this paper was just had tough time to find all the possibilities to get this one phase into it, right, with a minimal extension of the standard model. And one was just to invent the Sir family. And when you go to supersymmetry, you double the particle spectrum, you have a natural minimal supersymmetric standard model of 45 additional CP phases. And now the question is, how it is possible that supersymmetry is at the 1 TeV level, right? There are new physics particles there. And why these 44 CP phases are not active in our refactory data. Okay? Why there were no sign for these additional phases. Why we were able to describe everything by this one phase in the CM matrix. We don't need any of these CP phases in addition. Right? So what it turns out, if you go to any other model which solves the hierarchy problem, you get a CP problem because you have a lot of, naturally, generically, you have a lot of new sources for CP evaluation and also for paper change, and you have no idea why they're not active. Okay, that's the problem. So probably these extensions which solve of the standard model, which solve the hierarchy problem, they get very often a new problem by solving one problem, namely what we call the flavor problem or the CP problem. Okay, next slide please. Now let's stay first today with the standard model and look how CP evaluation is described in the standard model. Now I want to go more in details. When you look here at the gauge sector, you know what, when you have the gauge theory, then you see that CP is a natural symmetry of the gauge theory, which is massless. How do you see this? So this is just gauge interactions, and then we have the coupling to the left-handed fermions, and there's no coupling to the right-handed fermions. You see that because this is just a derivative. Here you have the covariant derivative, which includes the gauge bosons, right? So, what is the standard model? The standard model is a chiral symmetry, where only interactions of the gauge bosons are given with the left-handed fermions and not with the right-handed fermions. Okay? Right? So what happens is that this Lagrangian violates parity of right-handed fermions do not couple to gauge bosons. It violates charge conjugation because left-hand antifermions do not couple to gauge bosons, right? But it preserves CP because both left-handed fermions and right-handed antifermions couple to gauge bosons. So what does it mean? If you do not include massless particles, no Yukawa couplings, then a massless gauge series is invariant on the CP. It's a natural symmetry of a chiral gauge series. And the standard model is chiral gauge symmetry, but it's of course not massless. Slide. So just to show you this again, let's look at pion decay. The weak force breaks C and P maximally. It means the pi is 0. It's made of up quark and anti-D quark. I give you here just the electric charges, because they're best known for you. And you see this goes via a W exchange, goes to the antimuon and a neutrino. And you see the antimuon is right-handed and the neutrino is left-handed, right? So I just described that by these arrows there. Now we make a parity transformation. What happens? The parity transformation transforms the antimuon to a left-handed antimuon and the left-handed neutrino to a right-handed neutrino. Okay? And this all stays the same. And then we make a charge transformation, charge conjugation. So you see the antimuon goes into muon and neutrino goes to antineutrino, but this antineutrino stays left-handed and the muon stays right-handed. Okay? By this transformation. So what happened is now, to the slide. So, as you know, this does not occur here, right? This process. Okay? So that's what we mean is that C and P are maximally broken. It's not that this process here has 60% occurs, 60% probability, and this has 40% probability. This has some branch ratio, and this branch ratio is 0. Also, maximum breaking of C and P, because this is the C transformation, and only this process is possible and the other not. Okay, that's what we call a maximum breaking of C and parity symmetry by the weak interactions. So only boson couples only to left-handed fermions and to right-handed antifermions, and this process never occurs in nature. Okay, let's come to the next slide. So you like these Escher photos. This can explain to you what it means. The law of weak interactions is that the white birds always go to the east, right? That's the law of weak interactions, and the blackboards always go to the west, right? That is the law of weak interactions. When you make a parity transformation, you come into a not allowed situation. Maybe there, that is one or two of these white birds would go to the west, and blackboards go to the east. But if you make a charge conjugation, you come to a situation which is still allowed by nature, namely now the black birds go to the west again, and the white birds go to the east. And what I mean with charge conjugation means I have just changed the color, right? It's a color charge, right? Yeah. Okay, so it's nice and simple. And you know this is possible here, but this situation is not possible. And what it means, maximum breaking of the symmetry, means it's not so that 100 white birds go to the east and there's one bird goes to the west. No. White birds always go to the east, black birds always go to the west. Nothing else is possible. Okay? However, now when you compare these two pictures here, this would be a CP transformation, right? And CP is also broken. And the funny thing, in this situation, you see even a little breaking of CP violation, of CP invariance. If you compare those, they look very simple, right? They're very, very similar, right? Because everything now is completely analog. But is there anything which is different in this picture and this picture here?
So it's shifted, no?
No, shifting means it's all over the sky, right? So it's all covered. The whole horizon is full of birds, right? So,
white parts of black birds and black parts of white birds are also.
Anybody? Normally there's one person who sees the difference. But we can keep it, so we can think about it. So we will put this on the net, and then you can see it tonight. And if you see a CP violation here between these two pictures, let me know. Okay? So next slide, please. But the difference, of course, let's just go back. No, the difference, of course, here is that
the tail.
the tails. Okay, yes. Right. You see here that the white birds, the line goes up, and here the white birds, the line goes down. And this is the result of the parity in the charge conjugation, right? And this tells you C and P are maximally broken by the weak interactions, and CP is only broken a bit, right? So that's what you learn from this picture, okay? But now there was at least one person to see it, right? So you see the tires goes up here, and here goes down. Okay, good. This is a little CP violation you see in the sun model. Okay, only a little bit. Good, thanks. So, some more basics. So, just gauge group, SO3 is 2U1. Fermion representations, we have the lepton fermions, and now I give you the quantum numbers compared to these three gauge groups. Right? So that's you probably learned last week. So you know the left-handed quarks are a triplet regarding the strong interactions. It's a doublet regarding the SU2, and the hypercharge is 1/6. Right? The right-handed quarks, up quarks, are a triplet regarding SU3. It's a singlet regarding SU2. They don't take part in the weak interactions, as we have just learned, and the hypercharge is 2/3. And the right-handed D-type quarks is a triplet regarding SU3, a singlet regarding SU2. Again, the right-handed D quarks do not take part in the weak interactions, and the hypercharge is 1/1.3. And you know there's a combination here which gives you then the electric charge of the disintegrate. And here, the leptons, here you see there's singlets regarding the SU3 and doublets regarding SU2. This is a doublet with an electron trino, and also those three families. And then we have a right-handed electron, or right-handed muon, or right-handed tau, which are a singlet regarding SU3, a singlet regarding SU2, and they have a hypercharge -1. Okay?
Can I make very brief comment?
Yes.
Remember last week we said Q is equal to T3 plus Y/2. Here hypercharge normalization is Y/2, redefine Y/2 as Y. Hypercharge normalization is arbitrary anyway. So in this normalization you have T3 plus Y.
That's right. I use another one, and I think it's good because it shows you that it's not fixed. Possibly this is fixed by gut series, but not in the standard model, right? So there's, as he said, the normalization is not fixed. That's a good reading. Okay? And what you see here, this I here, this is important. So this big E I here is the interaction eigenstates, right? Before electric symmetry breaking. And this I here goes 1, 2, 3 is just the flavor index, right? Because it goes 3 times. You have the left-handed doublet for all 3 families, right-handed up and down for 3 families. So this I runs from 1, 2, 3, 1, 2, 3. Okay? Right? And now you learn about spontaneous symmetry breaking. I have here the Higgs sector. This is also a singlet regarding SU3. It's a doublet regarding SU2. And you assume there's a vacuum expectation value is fixed by this value here, and then the gauge symmetry of the standard model is broken down to the SU3 color charge and the U1 electromagnetic. So this you have learned last week. And then you see what is the gauge interactions of the left-handed quarks is given exactly by this Lagrangian here. The left-handed doublet couples to the gluons, to W, and also to the gluons. So, and this is, as we have learned, CP conserving. There's no if you have no masses, we learned at the beginning, you have no CP violation in both. Okay? This is because you can write down now the same for the right-handed up quarks and the right-handed D-type quarks, and they have the same term written here beside the coupling to the W and the B. So everything is the same, but there is no CP violation possible. Right? So that's the next slide. CP violation comes only into place when you now look at Yukawa couplings. Yukawa couplings, which are compatible with gauge symmetry, is the following. So the left-handed quarks coupled to the doublet, 2 doublets on a singlet, and the D is also a singlet grounding SU2. So this is a gauge invariant combination, and this is here for all family families, I and J. This can be different, so you have generally a 3x3 complex matrix in front of it, which are called Yukawa couplings, and as I told you at the beginning, these couplings are not fixed by gauge invariance. So that's what I called you the standard model flavor problem, that we have no deeper understanding of this structure here. Right? You fix everything by gauge invariance. This is fixed here by gauge invariance, this coupling, right? There's no other thing possible. So this is a doublet, this is a doublet, SU2 doublet, and this is a singlet. So this is something invariant. And in front, I have now a 3x3 matrix, which is completely unfixed by the gauge invariance. Okay? So we have no deeper understanding on this Yukawa couplings here. We have this in the D-type sector and the U-type sector. And now I just give you the result of the paper of Jan-Skirkis, that CP violating occurs only, and this is a necessary and a sufficient condition, that the Yukawa couplings, the determinant of this commutator of the Yukawa couplings, is just real. Right? That is one thing. Okay? Normally people say it's enough that Yukawa couplings are real. That is definitely a sufficient condition, but it's not necessary because there are unphysical cases involved. That's a crucial point. So CP violation is related to complex Yukawa couplings. So the hermiticity of the Lagrangian is given by this. So you always look at the Lagrangian plus the hermiticity conjugate. So we take this one term here, take hermiticity conjugate. Now we make a CP transformation, which makes exactly this left and right, exchange left and right, and make a hermiticity conjugate of this Higgs field. And then you have CP invariance if the Yukawa coupling is real. Right? This is definitely a sufficient condition. However, now we should keep in mind that in this Yukawa coupling there are unphysical phases which you cannot observe. And if the complexity of the Yukawa coupling comes from these unphysical phases, then you still have CP invariance. Okay? This means that this condition here is not necessary. It's only sufficient for CP invariance. Okay? So next slide. So Yukawa couplings are the only source of CP violation to Stern model. That's one thing, because the gauge sector for spin breaking was completely CP conserving, as you learned. It's really this term here in the interaction basis, and everything is written in the interaction basis, which includes or brings CP violation in. Okay? And this comes from the complexity of the Yukawa couplings, but I gave you already, there is a caveat involved that there are unphysical cases in the Yukawa coupling. We'll learn more about it in the other cases. Let's come to the next point. So, what I can do now, I can use this, and Yukawa coupling is the only source of violation in the Stern model. And this comes from the fact that we have a flavor symmetry. So let's go back. Do I have to go back first? Is it possible? Oh, no, I mean that I can just press buttons.
Ben basarım düğmeye. İleri geri
Really? Sorry, I don't want to make you worthless, but one is just better. Because if I told you, because you see, I have just do it like that.
Geri gelirken kendim alırım diyor. Öyle daha rahat olacak. Tamam.
That's fine. And then we just, okay. And you press these buttons here. Okay. So probably it's better because then you can, because I've explained to you. Just have a look at this. So what I want to express is the following here. So there is, I have to explain to you where the U3 invariance is coming from. The reason for this is the following. These are three unitary transformations of these three families. And you have one for the doublet, and you have one independent U3 for the D, and an independent transformation for the U. And this is on the gauge sector. If you look at this, you see this. This is the gauge part of the QL, okay? Left-handed doublets. And here you have the I, and here you have the I. So then you make now a unitary transformation on this three doublets here. It just cancels out. You see this? Okay, so I should write it down. So you have something like QLI, and then I make a transformation, 3x3 transformation, which is IJ, unitary transformation, U3 on it. And then you make also a transformation on the second one, on the other side. Okay? So you write here you write a Hermitian, and here's a Hermitian conjugate, because this is just the dagger. Then you have here Q, this is then J, K, K. Okay? And this is also the left-handed. You see this? So, and this transformation, you know, that is, it's a unitary transformation. This is just the one, okay? So you can make a unitary transformation on the left-handed, three fundamental left-handed quarks, and you see that the gauge part is invariant on it, okay? So you can do the same if there's a right-handed up quarks and if there's right-handed down quarks, right? You have the same interactions without these gauge terms. Okay? You see that? Then we have here just the DR on both sides. Again, independently, you find another unitary transformation. And everything on the gauge sector is invariant. Okay? So this means we have in the gauge part of the standard model, when the Yukawa couplings are 0, you have a U3, a U3, or U3 symmetry. So that all of those can be independently transformed, right, without changing the gauge part of the standard model. So this means a massless standard model has this chiral symmetry, a U3, U3, U3. Okay? That's obvious. Now, Yukawa couplings, when you put in the Yukawa couplings, this is broken. Because if you look at this one, if you do not make a transformation, you see this gives you a transformation on this left-handed, but then here you have the transformation on the right-handed equals. And this is not invariant because these are two independent unitary transformations. Okay? As we said. The same is true here. If you make a unitary transformation on the left-handed and another unitary transformation on the right-handed upwards, this is not an invariant term. Okay? So it's clear that these Yukawa couplings, which are responsible for the masses, are not invariant under the U3, U3, U3 symmetry. Okay? You see that? Good. Then, what is left over, however, these symmetries are completely broken, but there is some symmetry left over, which is a U1, which means that the number of quarks and the number of antiquarks is still the same. This is what we call baryon number, right? So it's clear that this term here, the number of quarks and the number of quarks is preserved in this term, right? This annihilates quark and this creates a quark. So this is the number of quarks is definitely preserved, but not later. Okay. So it means that after the Yukawa couplings are there, this symmetry gets broken down to U1, which corresponds to the baryon number, which is just symmetry corresponding to one parameter. Okay. Now, this allows us to see what are the physical parameters in the Yukawa couplings, because what I can do now, I have the Yukawa couplings, and make now a transformation of the gauge part, and then I get a physically equivalent set of Yukawa couplings. If you look at the Yukawa couplings, on the one hand, you get a unitary transformation of the left-handed, and on the right-handed equals. Here you get a left-handed unitary transformation and the up unitary transformation. If you look at the transformations, Yukawa couplings, you see that's where it comes from. If you make a transformation on those and those, then the Yukawa couplings change. And if you make a unitary transformation on this and on this, and the Yukawa couplings change. So the only change is exactly that you get new Yukawa couplings with these two unitary transformations. Okay? However, the gauge part is invariant under these transformations, which means that you get two physically equivalent set of quark Yukawa couplings when you go from here to here. Because the gauge part is invariant under it. You got the argument? So what it means, this allows us to count the number of physical parameters. Namely, you start with two Yukawa couplings. These are 3x3 matrices. This gives you 9 parameters. If you have 2 of them, it gives you 18 parameters. But they are complex parameters, so you have 18 multiplied by 2 real parameters. Okay? So you have 36 parameters which are not fixed by gauge invariance in your standard model equation. So that's a lot, right? So you know that not all of them are physical. Now, you can make 3 unitary transformations here on the gauge sector. Okay? Means you know that one unitary transformation has 9 real parameters because you have all these unitary relations. Gives you 9 multiplied by 3, which you can reduce it because you can always do this transformation without changing the physics if you do it equivalently. So it means that you had 9 multiplied by 3 unphysical parameters. 70 is 27. However, one of these symmetries is left over. So you have to add 1 parameter again. This gives you 10. And of course now you can think about it. Some people know already that the CKM matrix has 4 physical parameters and we have 6 quark masses. So that's 10 physical parameters, right? And this fits exactly to this 10 physical parameters in this Yukawa coupling. But it's very difficult to see them, to make them visible, right, in this Yukawa coupling. Now we're counting by using the symmetry. You got the argument? Right? The argument comes from the fact that these two sets of Yukawa couplings are equivalent because after these transformations, the gauge part is completely unchanged. Okay? Good. Now, the complex comes to another statement. The complex space in the CKM matrix is related to the equivalence. Now, we go to the mass eigenstates. Right? Before everything worked, to check, use now, this was all interaction basis, which is given by this big I here. Now we go to the mass eigenstates. You know, you need now the unitary, the CKM matrix, and this was explained to you last week, how to get this. And when you have done it, then you get the mass eigenstates. So if you make electric symmetry breaking, then these mass 3x3 matrices are given by the vacuum expectation value multiplied by the Yukawa couplings, right? There are still interaction eigenbases here, and then you translate them, diagonalization mass matrices by unitary transformations, and then you make them diagonal by transformation of the right-handed quarks and the left-handed quarks. Okay, and that was shown to you last week. So what happens to the gauge interactions? Now we have the mass eigenstates here, not the interaction eigenbases, and then we have two unitary transformations here, which give you the CKM matrix. Okay. Now the mixing is not, the gauge interactions are not flavor diagonal any longer. The mixing is now in the gauge interactions. Okay. After going from the interaction basis to the mass eigenstate basis. That's the crucial point you should see here. Okay. So this is just a CKM matrix. Now after this, unitary transformations are left-handed and the right-handed quarks with the same matrix. You see that you get the CKM matrix, which is also unitary, and this tells you now that the charged transformations are not gauge-full interactions are not flavor diagonal any longer. Now, so it means circulation is correlated to the CKM matrix. How we can see this? We can say this is again CKM matrix. It's a unitary transformation, so it has 9 parameters. However, I always can add here a diagonal matrix here. What I mean with this PQ is something like E I of 1, E alpha 2, E alpha 3. Right? 3x3 matrix. Phase matrix. Right? So I can add this without changing anything, because if you see, it just cancels out. If we use the same for left and right, you can multiply this by this space matrix and without changing anything. Which means that these spaces are unphysical, because you don't change anything here in these matrices, in the CKM matrix, in the physical interactions when you add these phase matrices here, which are diagonal. So they cancel out in all interactions here. You see that? The important point is only that you use for the left-handed and the right-handed the same. Okay? And then you have for the up quark and for the down quarks, you can use them differently, right? So if you for up quarks as 1 out of 3, and for the down quarks you have 3 other phases. Okay? But as you know from quantum mechanics that you are not only sensitive for relative phases and you transform these things without changing the physics. Okay? There's only one relative phase which is really physical. Okay? What does it mean? It means that we have 9 CKM parameters because it's a unitary transformation, but you can get rid by these phase transformations 5 relative phases. Okay? So physical parameters of the CKM matrix are, after these phase transformations, are only 4. Okay? And of course, we have the diagonal matrix, which is unchanged by these phase transformations here. So we have 6 quark masses. We have 6 quark masses, 4 p-meters. Again, you get these 10 physical parameters. So you know, and that's you should know that when you do electric symmetry breaking, you do not change the physical system. It's just a reparameterization, right? So the number of physical parameters should not be changing by electric symmetry transformation. Okay. So that is what you see. I have given you an exercise where you work out these spaces here, right? Because that's rather important that you see what is physical, what is non-physical. This is a nice exercise to see what are these transformations I give you here in detail to find out what are the physical parameters. And I think this is a problem which always occurs again and again when you go to a new physics model to separate the physical parameters from the non-physical parameters, right? And I think the argument I gave you before is also something which you should keep in mind, that you see something, you have one part of the Lagrangian which is invariant, and then this shows you that if you use the transformation on the other part, you get two physically equivalent sets, right? That's important. It's an important argument which is always comes up again also when you go to new physics. Therefore I think it's important that you learn this. Okay, now we come back to CP violation. If you look at the charge current interaction Lagrangian Mersenne state basis, it looks like this. This is the CKM matrix. This is the left-handed up box, left-handed down box, and this is the charge current interactions. And now the point is one representation of CP. I've used it before. The W plus goes transformed into W minus, and the current gets here exchanged. 1, 2 gets exchanged to 2 and 1. That was the transformation. Is one representation of the CP in the Hilbert space. Now, if you look now at the Lagrangian or the charge current interactions, right? You see here you take the Hermitian conjugate of this term. So the Lagrange should be always Hermitian conjugate. And then the question is, if now the CP transformed one, you see this is CP transformed one from here to here. This term goes to this term, and this term goes to this term, okay? And you see when V is real, the CKM matrix is real, then the whole thing is CP invariant. You see that? So use these transformations on these two terms, then this term goes to this one, and this term goes to this one. However, it's only the same when the CKM matrix is real, okay? Now the question is that a necessary condition? And I say no, because there are, as we just learned, unphysical phases involved in the CKM matrix. So it could be that the CKM matrix is complex due to unphysical phases. Okay? So it's not so. When the CKM matrix is real, means we have CP invariance. But if the CKM matrix is complex, it doesn't mean that we have CP violation. Okay? So that's, the argument is more involved because they are all phases of the CKM matrix are not physical, as you just learned, right? So what you do for this, and that's a bit more technical, and I put it also on the exercise sheet for today, probably more for the series, that you look at refacing invariants, or combinations of CKM matrix elements which are invariant under these phase transformations here, okay? Where we know that they're unphysical. And it's obvious what are the combinations which are invariant. And these are the direct observables. So it's important to find out what are these invariants which are really correspond directly to observables, right? Because they don't involve any kind of unphysical parameters. So the modeling of the CKM matrix elements are definitely phase invariant, because if you make these phase transformations on this one, on the alpha and to the I, they cancel out. Because the modeling is just given by I, and then this cancels out, right? Because you get the Hermitian conjugate, and then you get here minus, and then these things cancel out. Okay? Now, the other way are the so-called quartets. These are combinations of 4 CKM matrix elements, and you see what are the quartets. You have the alpha here with the CKM matrix, and the alpha occurs again with the Hermitian, or the complex Hermitian conjugate part. So this alpha gets this phase transformation, and the other alpha gets the same phase transformation with a minus sign. So you see that all indices are correlated in such a way that I here goes with V, and the other I goes via V star. It's a complex conjugate. Okay? You see that all phase transformations on the different parameters here cancel out. So these are phase invariant. Everybody sees that? Probably not. So, but I would guide you to the exercises to really think about this, and then you see that these are the placing areas. But it's important to write these things down because they are completely now not related to unphysical parameters and can be direct observables. It's clear that any kind of observable has to be written in terms of these two kind of parameters of the CKM matrix, because the crucial point is that all invariants of higher order can be written as functions of these two kind of CKM matrix elements. So that's the crucial point. There are singular cases which do not occur in the standard model. So that's only a remark for the mathematicians. Okay? So what I can do now is, it's more in the technical part now, I take the most general CP transformation, which leaves invariant all terms of the Lagrangian except the charge current interactions. Okay? And write this down. You see, these are the most general CP transformations. On this, it's not just the one we have written down. You see there are phases involved, which are just the unphysical phases, which you can write down without changing the physics, which cancels out. And then the CP invariance of the charge interaction constrains the CKM matrix. You see the condition you get out of this is not that V alpha k has to be V alpha k, without a complex, but you have unphysical phases involved. It means that CKM matrix has to be real up to unphysical phases. And this means that all phase invariants of the CKM matrix elements have to be real. And that is now not only a sufficient condition, but it's also a necessary condition. Okay? So CP invariance requires that all refacing invariant combinations of CKM matrix elements are real. And this is parameterized parameterization independent criterion, right? So it's not enough to say the CKM matrix has to be real, because there's thousands of different representations of the CKM matrix, right? You can make many transformations. The crucial point is that these quartets, right, which are refacing invariant, which are not sensitive to these unphysical phase transformations, have to be real. That's the sufficient and necessary condition, right? It was a bit more, just I want to show you things are more involved, and what people now say is not completely true. So, parameterization independence of evaluating quantity of the CKM matrix are just, so if the imaginary part of these phase invariant quartets is non-zero, then this is the CP evaluating parameter. And it turns out you can write down any kind of quartets. They're all just proportionally to one parameter, which is the famous Janska parameter, and the epsilon tensor here, which gives you 1 or minus 1. Which means, it turns out that all quartets which you can write down are all equal up to a minus sign, because they're all equal to the Janska parameter. And this you can show, and I ask you to do this also in the exercise. If you write down the unitary relations, you can show that all quartets are the same up to a minus sign. Think about it, how you can write, derive it from the unitary relations. Right? So it means also that any kind of unitary triangle, right, they all have the same space inside a unitary triangle. It's always just the Janska parameter, which is the measure of CP violation in the standard model. It's only one parameter. Okay? But to show that there's only one parameter, you have to show that all quartets, which you can write down, are related by the unitary relations and are just all the same up to a minus sign here. Okay? But that's what I leave for you to show in the exercises. And this proves that there's only one parameter in the standard model which are responsible for CP violation. And the parameter you can calculate, of course, in terms of the CKM matrix elements, and you find out that they're time minus 5. Okay? It's very small, and of course that was the little thing which you have seen in the Escher picture. It was also not a big difference, right? So not only one or two persons have seen it. So how much time have I got over? Let me see. So
8 minutes.
Okay, no, that's fine. So we can do now the Janska theorem for the weak interaction basis. We start with the Lagrangian in its initial form of the weak basis, and then all gauge terms are diagonal and real. Remember that? Okay, so you go back to the interaction basis. In the interaction basis, the gauge interactions were CP invariant. And then consider the most general CP transformation which leaves invariant the part of the Lagrangian containing the gauge interactions. And then check whether CP transformations defined gives the restrictions on the remaining Lagrangian, which is the mass Lagrangian. Okay? You can do the same. That was done by Mrs. Yalskak. And it turns out that the condition on the quark sector, the mass quark sector, is that this has to be non-zero. It means that all the mass differences of the quarks have to be non-zero. So it means if two mass parameters in the quark sector are the same, there's no CP violation. And this is an extra exercise I put also on the exercise sheet, which you can nicely derive. What does it mean? If you have two parameters, or for example, the top quark mass and the charm quark mass would be the same, and of course this parameter would be zero, and then the whole parameter is zero here. Okay. So what happens if the charm quark and the top quark mass would be degenerate? It means that they are undistinguishable, because we just learned that the charm and the top quark mass belonging to the second and third family. The only difference is the mass quantum number. So if the mass quantum number is the same, we cannot distinguish between them. Right? That the charm mass and the top mass, or the charm quark and the top quark is the same. So we can make a transformation between these two without changing the physics. And this gives you an additional freedom, additional phase, which allows you to rotate away the physical CKM phase, which produces CP violation. You can imagine this? Right? So if you have top quark equals to charm quark, in the sense that the masses are the same, then this allows you for an additional transformation between these two quark states, and this gives you another unphysical phase. And this unphysical phase allows you to rotate away this fourth parameter, the CKM matrix, and this allows you to get rid of the CKM phase in the standard model, which means we have no CP violation. Okay, so that's it's clear from the argument. However, we can derive this, and this is an extra exercise on the exercise sheet, but probably is only suitable for serious or theory-orientated persons to derive this. But it's important that you learn from this that CP violation arises as a clash between the CP properties of the gauge interaction and the mass term. You can make CP invariant as one term, but then the other one is not invariant, or the other way around. Okay? And if you just assume this, that you find CP transformation on the other, get conditions on the other Lagrangian, and you were able to derive this condition here. So, which we understand. So the requirements on this standard model to violate CP is that within each quark sector, no mass degeneracy is allowed. But of course, we know from the experiment that this is not the case. Okay? None of the three mixing angles should be 0, pi over 2. You will see from the parameterization I give you on the exercise sheet that would also be imply that the Yalskak parameter would be 0. And then the physical phase should not be 0 or pi, because 0 or pi is not a complex number any longer, and then also the CKM phase disappears. Right? So these are the conditions for having CP invariance in the standard model. So we have learned that this is not the case already. So we have a CKM phase, but I think the argument is a good one to learn how to, for example, address the same questions. We go now to a new physics model and look at the flavor structure, and then you have the same problem that you have to separate the physical parameters from the non-physical parameters. And I think that's a good example which you know well, and where you can now use the argument again, and you go beyond the standard model. Now, this is a standard parameterization of it. So you get, this is a cosine of theta, and this is a sine of theta, and it gives you 4 different parameters, and there's 3 parameters, and then you get 1 delta, which is just the phase. This is a parameterization which was used in the original paper, and as I told you, it was written in the wrong way. But there's another one which shows you the hierarchy of the charge current processes, right? So if you have a charge current process which U and D combines, then you get something like 0.22. when you look at something which corresponds from the first to the second family, then you get something of order 10 minus 1. When you go from strange quark to top quark, you get also something of order 10 minus 2. And if you go from the first family to the third family, you get a CKM factor which is suppressed by 10 minus 3, corresponding or compared with the diagonal elements. Okay? So you get a strong hierarchy which is involved in those parameters here. We can make them more manifest by using a different form of parameters, lambda, a lambda squared, and this delta, rho and eta, and then the hierarchy of the CKM matrix elements are manifest, right? So you make an expansion in this parameter lambda, which is 0.2, and this is done only to the fourth order. The precision of the data needs the fourth term already, but you can make it higher up, right? So in the expansion, you see these are of order 1, this is of order lambda, this is of order lambda squared, and going from the first to the third family gives a lambda over 3, right? You see, this way the hierarchy of the CKM matrix is manifest, and as we told you at the beginning, we have no idea where this hierarchy comes from, right? Because of the hierarchy of the unitary relations, as I told you, we have 3 relations, and you have another 3 relations if you look at the rows. So you see this one here, because of the hierarchy of relation you can now write down, you see that it's not a nice triangle. So this one here is lambda 3, lambda 3, lambda 3. That's the one I showed you. So then all sides are equally sized. Why, if you look at those, this lambda, lambda, lambda over 5, so it's a very flat triangle, right? So it's very difficult to measure these angles, which are almost 0. The same is true for this triangle here. It's lambda 4, lambda 2, lambda 2. So there's one side which is very, very small, right? So this favors this one here for experiment in the first one, because here all sides of the triangle, unitary triangle, are the same size, the same order. And so another crucial point, we have learned what are the replacing invariants. Okay, these are the quartets Q, and what you can derive is that the angles in this unitary triangle can be expressed in terms of the quartets, which means that they are directly observable. Right? This is always a proof, because we learned that the CKM, only the phase invariant combinations of the CKM matrix elements are directly observable, and if we show that alpha, beta, gamma, which are the angle in the unitary triangle, comes from this third one here, which is 3 sides almost the same, then you see they can be expressed in terms of these phase invariant quartets, means they're directly observable. That's the way to prove this, okay? Because you get rid of unphysical parameters. Then an addendum, CKM matrix with n quark families. So you know why you went from 2 families to 3 families, because only when you go from the case with 2 families to the case with 3 families, you get a CKM phase. So we can do the counting and assume you have how many phases you have when you have n families, right? So generally, n by n matrix has n equals squared parameters. Redefinition of the quark fields gives you 2n minus 1 arbitrary phases, right? So minus 1 because 1 relative phase is physical. These are the phase transformations. And the physical parameters then are n equal 2 minus 2n minus 1. So it means n minus 1 squared, right? And this is true for our case, because here we have 3, it's just 2 squared, it's 4 parameters, right? That's exactly what we have shown before. Now, and just to prove, no CPU relation possible with 2 families, because then you have only 1, 2 minus 1. You have only one angle in the Cabibbo matrix with 2 families, right? And there is no phase, complex phase, which can produce CPU relation. Okay? This shows you what was the content of the Nobel Prize, right? So going from the 2 family case, where no CKM phase is involved, going to 3 families where you have an additional phase, okay? Which can produce CPU relation. It turned out that was one option they offered to the public. Now, at that time when they made this argument with the third family, there's a consistency check in the argument. This was 72. In 72, the tau was not found yet. However, I just want to give you the argument, and you found the third family in the lepton sector, it's clear that you also need the third family in the quark sector. Because there is something, when you calculate radiative corrections, there are something like anomalies, right? The anomalies is something that you start with the symmetries, which are the gauge symmetries, which fix you the standard model Lagrangian. This is your defining symmetry. Okay? These are the gauge symmetries we started with. When you now calculate radiative corrections, it's important that these radiative corrections are compatible with these defining symmetries, because you have otherwise an inconsistency in your theory. You understand that, what I mean? So you start with SU3, SU2, U1, and write down the most general Lagrangian. Okay? This is your defining theory. When you now calculate radiative corrections to this, right, in quantum field theory, and these radiative corrections are not compatible with your defining symmetry, then you would say, oh, that's not a consistent theory. It should be possible that the radiative corrections are all compatible with the defining symmetries, the defining gauge symmetries. So if the symmetry is broken in higher order by radiative corrections, we call this anomalies, right? Because it's not what we want, right? We call this anomalies. So it's important that all anomalies in the radiative corrections cancel each other, so that the symmetry which defines our theory is preserved also in higher orders in perturbation theory, or say by radiative corrections. Okay? So I get conditions for the cancellation of anomalies in quantum field theory. It's a very technical point, but it was very important for model building at that time. Right? So this radial consistency of the sum requires that such anomalies do not occur. Right? With this also clear, because if you define this theory by symmetry and the symmetry is broken, when you work out the symmetry, then you would say, well, that's not what I want, right? So the necessary condition for the cancellation of possible anomalies is the fact that the number of lepton families has to be equal to the number of quark families. And one condition, necessary condition is that the electric charge of all fermions with one family has to be 0. So what you can calculate this for one family. So for electron and neutrino, then we have the up quarks and the down quarks. Now we calculate the charge in one family. So the charge neutrino has no charge, electric charge, so we have only -1 the electric charge from the electrons in one family. Then from the up quark, you know the charge is +2 over 3. Okay? But then you have a factor 3 in both. You know, and this comes from the color, because you know the up quark comes with 3 different colors. So there's a colored quantum number. So in one family you have 2 or 3 multiplied by 3 up quarks, because 3 different colors, multiplied by E. So if you calculate this, it gives you +2 the electric charge. The units given by the electric charge are very. Now the B-type quarks gives you also -1 over 3 multiplied by 3. And the 3 is not the number of families, it's the number for one family, right? But you have the color. The color quantum number gives you 3 degrees of freedom. So you get -1. Now we add up. This is -1 plus 2 gives 0. Okay? So this relation here, that the electric charge of all fermions within one family has to be 0, is important for this radical consistency of the standard model, that those anomalies disappear. So, you have a question? So, this means when you have found the tau already, which is a member of the lepton family, then you know there's also a third family of the quarks, right? You don't have to postulate this. However, and this is why they got the Nobel Prize, the tau lepton, as the first evidence of the fourth lepton family, was found in 1975, which is after the Seeker paper, by Pearl, and he got also the Nobel Prize for this in 1995, already before the others. But when the tau was found, it was clear there must be a third family. Okay? to clear to you, right? So this comes from the theoretical consistency conditions to the gauge theory. So that was another side remark, but now I probably should stop here, right? And we come to the different kinds of CP relation later. So when you have some questions, let me know now. Yes?
Is it true for also the Biot standard model like theory that leptons should have quarks? If there's a lepton of fourth family, there has to be a quark.
It depends now, right? Because if you go beyond the standard model, then probably the condition gets weakened, but also strengthened. It depends on the model, right?
Yeah, but
so because if you add new degrees of freedom, there are more chances to make cancellations, right? But on the other hand, it could also be it's more complicated. And it's difficult to say in general, right?
So there can be like 4 families of quark, but still 3 families of leptons, for example?
If you just add a fourth family of leptons, this doesn't work. That's exactly the argument here. So you have to do something more, right? So because the argument is, then you add, because this argument was given for one family, right? So if you add now, I don't know, a fourth family tau, right? Whatever, then you have here a charge, and no charge is here, and this doesn't cancel, right? So then, this was a minimal extension of the standard model. This one lepton family doesn't work. That's exactly going from 2 to 3. The same argument is true for going from 3 to 4, right? So if somebody now founds a fourth lepton, charged lepton, or a fourth neutrino, it's clear there must be also a fourth family of quarks. Or there is something more complicated that you get much more particles, and this necessary condition is not necessary any longer, but it's rather complicated to construct things like that. So I would think that this argument is still true, that the number of metric charges add up to 0 in each family. Okay. Any other question?
If there is mass degeneracy within the same generation, does it still imply no CP violation?
Yes.
So
this is also true, right? Because I think there's a good question. So if up and down quark are equal, so people put this to 0 for the strong CP problem, then you have a problem, right? Where was that? Here, you see that there are all differences, right? Yes. C, E, S, E, D, S, E. Right?
So there are differences between up type and down type.
Right. So
you
you
think about the same mass for the up and down particle.
That's right. No, that's right. You're right. It's not true. Right? That's right. No. Good that we checked it. Right? So you see, this is the condition. So it's within one charge. Right? So
one sector.
One sector, right? So top and charm has to be different. Charm and up quark have to be different. This is clear, right? And the B and S, B and D, and S and D. You see, this is all between only one family, right? Okay. And actually, I'm really missing something here because S, B, D, S, D, B, S. So the top and U is missing, right? So you already found your typo. Okay. But it's good that you asked for this because it's true that it's not CP validation is still CP validation possible. So I take back what I said; it was wrong. So if up quark and down quark, or the B quark and the top quark is the same, it doesn't matter. So it's just in one charge sector. Okay, this was. Yeah. So you see, you have to be very skeptical. All what I say, right? So, but there is definitely one term you missing. It's also, it would not, also the argument I did before would not work, right? Because if the up quark and the down quark has the same mass, right, then they are not degenerate fields because they have one difference still, namely charge, right? So the argument we used before, then they have a free phase to get rid of the CKM phase, doesn't work, right? From that, I think you could already argue that this cannot be the case, right? So if the up quark and the down quark have the same mass, they have still a difference between the electric charge, and they are not degenerate as the complete states, right? There's still a difference, so there's no general unphysical phase between them, which becomes unphysical, right? There's still a difference. Okay. Okay, there's no further question, so what I think we're going to have this paper which you pick up.
Let's break for tea for 15 minutes. During the break, you can pick up the homework from next to the photocopier, actually, from that desk. Also on that desk, you will find a number of evaluation forms for this school. Please take them. The idea is that you fill the evaluation forms whenever you feel like it, but you drop them anonymously, obviously, before the end of the school. Or maybe you wait until the last day and you give on the last day. Also, next to the evaluation forms, there are some old style paper agendas there for free for you to take help yourself. And the next lecture about Hurth will be in the computer lab in the other building.